we were discussing noise in active mixers. So we started off going from the easiest to analyze to the more tougher one. Obviously the easier one to analyze is the load. It acts directly at the output. It doesn't matter whether you are looking at the output referred noise or the input referred noise. For practical purposes, you are worried about the noise at the output. You can always divide it by the conversion gain of the mixer, refer it back to the input and figure out the noise figure of the mixer. So whichever one is useful to you, you can use it. Just remember that unlike other systems, the input frequency is not the same as the output frequency in a mixer. That is the important thing to keep in mind. So the first noise source we started analyzing was the noise from the load. If it is a down conversion mixer, you will have a resistive load most probably, and we know the noise from a resistor and the headroom versus bias current versus noise trade-off with resistive loads. In such a case, the noise spectral density is nothing but 8 kT RL in the voltage. On the other hand, if you decide to use an active load with you can use either a PMOS or maybe a PMOS with a common mode feedback, and depending on that, your headroom issue is solved. Now you need to worry about the noise from the PMOS devices. For example, if this is a down conversion mixer, then the PMOS could have flicker noise. You will have to worry about that. Whereas if you had used a resistor, you would not have flicker noise. So the noise from the load was very easy to analyze. What happens if it was an up conversion mixer? What kind of load would you choose to use? What kind of load would you choose to use in an up conversion mixer? The input is at baseband or maybe some IF if you choose a heterodyne transmitter, which is very rare by the way. And the LO frequency is high frequency. What happens to the output? What is the output frequency? Output frequency is a high frequency. It is going to be at FLO. Can you use the resistive load at that point? There will always be some parasitic cap at this node, and if you decide to use resistive loads, right, the bandwidth at that node will be very small. You will not get enough gain. Okay, 1 over 2 pi RC will be the 3 dB bandwidth at that node. And normally for the kinds of frequencies we are talking about here, those bandwidths will be too small. So you cannot use resistive loads. What else can you use then? You have to use inductive loads to tune out the parasitic capacitance. But of course, at the same time, you don't want to be at the mercy of those parasitic capacitances as far as the frequency is concerned. So okay, so you will tune it using an inductor. So you will have some tuned load. Does it produce any noise? So of course the tuned load will have some equivalent Q at your frequency of operation, and you can replace that using a parallel RLC circuit and RD, LD and CD, and the noise from RD will matter because the source of that resistance is a physical resistor. That physical resistor produces noise, and I have already mentioned this before. You can show that the overall noise produced by this is the same as as if you had a resistor RD. If the output impedance is RD at the frequency of interest, the noise produced that will be the same as that produced by a real resistor RD. Okay, so far as load goes, it's very straightforward. Next step is to look at the noise produced by the transconductor. That is also somewhat straightforward to analyze. So let us look at the noise from the GM stage. So and let us say the tail current was some IT, and this is your VRF, and this is your VLO to give your output baseband. So you are interested in the noise from this device. How would you analyze this? Ajmal, how would you figure out how do you analyze this for noise? Input impedance looking at which, so let me name these transistors M1, M2 and M3. You want to look at the looking at impedance looking into the source of M2 and M3. Okay, what will that give you? Okay, cut off. So you don't have to worry about one of them. Okay, but remember that it's a function of time. Which one is cut off and which one is on is a function of time. So is that really the way you want to look at it? So the noise here, the noise produced by VRF, as far as the transfer function from the input to the output, cannot be distinguished from the RF signal. Right? Whatever happens to the RF signal or whatever happens at the RF port, from a signal point of view, will be indistinguishable from what happens from a noise point of view. Right? For example, if I had said it had some noise here, what would you have told me was the transfer function? If I had VRF, what do I get at the output? I modulate it with the switching pair M2, M3, and I get a mixing action. What kind of mixing action do I get? I multiply your GM times VRF, which is IRF, right? So your IT plus IRF gets modulated by the switching pair. There is an S of T signum function. So the current gets switched on either side. We have calculated earlier what the overall transfer function is. What happens is the signal, this IT plus IRF, gets multiplied by a sum of sinusoids. So you have a sin omega LOT term, you have a sin 3 omega LOT term, a sin 5 omega LOT term, and so on. Obviously the amplitudes of these is also reducing because it's a square wave. Correct? If you had a noise VIN at the input, whatever happened to VRF, the same thing would happen to VIN also. Correct? So let us analyze it that way. So I am going to say it is the same as if you had a switch. So this is GM times VRF, but along with that I have the noise from IN. So let me remove this for now. I have the noise from M1, the thermal noise, the drain thermal noise. It could also include the flicker noise also. We are going to see both, what happens with both. So as before, we will say that IN1 gets modulated by S of t due to the switching pair. First of all, what does this mean? When we say it gets modulated, obviously it is going to get what? It's going to get shifted in the frequency domain. That is understood, right? So just as you shifted the RF signal from RF to baseband or IF, the noise signal will also get translated from RF to IF. Okay? So let us first look at thermal noise. So let us say this is omega LO, 3 omega LO, 5 omega LO and so on. This is my omega axis. And what does IN look like? IN is a broadband thermal noise. Correct? So let us say my input signal is here, omega RF. If I plot the output at omega IF, what I have, let us say, is some gained version, let us say, of the RF signal. Apart from that, what will I get? I have this portion of thermal noise which will add up. Remember, for any mixer I will also get thermal noise from the image band. Correct? So I'll have an image band which will also contribute to thermal noise. Anything else? I will get noise from around 3 omega LO, because the components around 3 omega LO will mix with the 3 omega LO component to actually come right on top of the IF signal, and same thing for 5 omega LO and so on, where each of these is omega IF. Correct? So each of these finds its way so on. So you actually get components from infinite bands of frequencies. Does this mean that the noise is infinite? Luckily no, because the amplitude of those noise components which are folding down keep reducing. So you have several sets of components, so on. But the thing to note is that these noises coming from different bands, different portions, bands of the around 3 omega LO, 5 omega LO and so on, they will add in power at the output. Okay? And they will have a certain transfer function which we can easily find out. What is the transfer function around 3 omega LO? Actually, what is the transfer function of the signal around omega LO? It will be the same as that for the basic signal. So let us write that down. So I'll say VON squared from the GM stage by delta F. This is the spectral density. I'll first take IN, which is IN squared, which is 4kT gamma by GM. This is the flat path spectral density times, what should I do? So first I need to multiply it by the gain factor. So for the fundamental one, that is 2 by pi GM RL the whole squared. Correct? This is for the fundamental. Is it only for the fundamental? It is actually for every component. right? This is a common factor. This 2 by pi gm was a common factor which you pulled out for all frequency components. Let us go back. Let's go to the single balance mixer. This 2 IRF by pi factor is a common factor for all frequency components. What is the other thing? Inside the brackets, the non-common components were 1, 1/3, 1/5 and so on for the omega LO, 3 omega LO and 5 omega LO component. So you can take this out as a common factor. 1 plus 1 by 3 square plus 1 by 5 square plus so on. Is that it? Is that all? I need to do one more thing. Into 2. Why? Why do I have to multiply it by 2? Because I get from both the upper sideband and the lower sideband. Times 2. Is that clear? So, as it turns out, this factor happens to be pi square by 4, right? So 1 plus 1/3, 1 by 3 squared plus 1 by 5 squared plus so on happens to be pi squared by 4. So this number can be simplified to be 4 kT gamma gm RL squared. Okay? This turns out to be a very simple expression. Yes.
When you get a noise, it goes, so there is some total noise.
Correct.
But this noise goes into the output for half of the time.
Correct.
It doesn't go into the output
for half of the time. Correct.
So the noise from the input, that since none of the noise is actually correlated with the switching frequency.
Yes.
We can see that half the total noise was over.
Okay. Correct.
So my point being that the noise from this thing is actually half the total noise.
Yes. So you could say that. Now, normally the only reason we analyze it in the frequency domain is because in the frequency domain you know that the particle density is constant. You know the magnitude of the particle density. It is just easier. But you're right. You can easily do it in the time domain. Correct. The two will give the same answer. And like that's what you said, right? It will give you half of this goes to one side, half of this goes to the other side in the other half cycle. If you analyze it that way, you will get exactly the same answer. Right? You will get exactly 4 kT gamma gm RL squared. So the noise from the transconductor, no, this is 4 kT gm RL squared. Okay, so the noise from the transconductance happens to be 4 kT gamma gm RL squared. If you have a double balanced mixer, okay, then it will have double this noise because you have two sources of noise getting added up at the output. Okay, if you have a double balanced mixer, you will have twice the noise. You do see a hit and noise figure, but it is much better because you are doing much better in terms of the LO feed through. Primary reason why we decided to go for a double balanced mixer was because of the LO feed through. If you have 1 over F noise, what happens? So, not exactly, because the supply noise does not get modulated by the switching pair. Right? It appears as a common mode noise at the output. That is all. Why is it anything else? right? If you're talking about ground noise, it's slightly different.
Yeah, in that case that will be
Correct. So let us say we have our omega LO, 3 omega LO, 5 omega LO and so on. This is my omega RF. Where is my flicker noise? My flicker noise is at baseband. Okay? So my flicker noise happens to be at baseband and not at RF and LO frequencies. What happens to flicker noise if I look at the output? This flicker noise gets modulated by omega LO, 3 omega LO, 5 omega LO and so on. So at the output, you get omega IF, but just like your DC, what happened to IT? IT mixed with the omega LO, 3 omega LO components to form LO feed through components at those frequencies. The flicker noise will behave in a similar manner. So at these frequencies, you will get 1 over omega LO component. Around those frequencies. Obviously in a receive mixer, this is not a big problem. As long as omega LO is much larger than IF or baseband, it does not present a big problem. What happens if you have a transmitter? You do have to worry about it, right? So it's not a big issue, but it depends on one important factor. What is that? When can you have 1 over S noise at the output? Huh? I'm not able to hear you. Baseband direct conversion receiver. No. I just said that direct conversion receiver is not a problem. If omega F goes to 0, all the flicker noise actually gets upconverted to LO. Right? It doesn't matter whether it's an as long as the IF is much smaller than LO, it is not a problem. So I said that it will get upconverted, right? But when does it not get upconverted completely? What happens if there is asymmetry in the LO between the LO parts? If it is not purely differential? It will have some DC component, correct? Similarly, it will also have a 1 over F component at the output. So if you have, it's not a big issue as long as symmetry is preserved. One over F noise in TX mixer gets upconverted to RF. So it is an issue. Okay? So we have analyzed the GM state, we have analyzed the load. The only thing left is to analyze the switching pair. Obviously that is going to be a little bit more complicated to analyze, because it is not as simple as just a mixing action. It is the mixing portion itself which is causing the noise. Okay. So let us take the case of the pair when, so let me just copy this first. So let us take the case when the switching pair is completely switched, right? So the signal is going to look like this, the signal is going to look like this. So in this region, M2 is on and M3 is off, correct? In this region, M2 is on and M3 is off. What is the noise contributed by M3? 0, because the transistor is off. What is the noise contributed by M2? Depends on the parasitic capacitance at this node. If Cp is small, then it is just like a normal cascode device and it produces very little noise because Cp is very small. If Cp was significant, then you could have more noise from the cascode, but for our simplistic analysis, we'll assume that Cp is small. Okay, so it is much easier. So there is very little noise from the switching pair after the device is completely switched. Similarly, in the other half cycle also, there is no noise from M2 and M3. So when do they contribute noise? During switching. Okay, because we know that they do not switch instantaneously. Okay, and therefore they have to produce some noise during that crossover time, and during the crossover time both of them may be turned on. Okay, therefore we have to worry about noise from both of them. So that is what we are going to analyze now. So the way we will analyze it is, if you had some noise from this M2 and M3, we will include it as an input referred noise at the gate of this differential pair. That is perfectly valid, right? Because this node is a virtual ground. Any drain thermal noise, we can refer it. Any drain thermal noise from both M2 and M3 can be pulled out as a single voltage source Vn in series with the gate. Correct? So I'll pull it out as some noise voltage Vn. Okay, so noise of referred to LO port. Referred to the LO port. What does this noise do? Suppose I have a noise source Vn. What is the effect of this noise? It changes the switching instant. When do the transistors switch? Suppose this noise were not present. Right? The transistors were completely noiseless. The transistors will switch. So let us say these were the overlap times. They would switch exactly in this region. Correct? Suppose I add a Vn. In fact, suppose I add a fixed Vn. What will happen? Let us say the Vn was positive in this direction. When will they switch? Suppose this is Vg2 and this is Vg3. So M2 is turning off and M3 is turning on. What happens to the turn on instant and turn off instant? It turns on. M3 will turn on a little later or a little earlier. I am adding a positive voltage like this. Okay, so what will the waveforms look like now? So let us say I am going to draw it like this. Okay, on the same curve with a blue curve. What will happen to M2? It will turn off earlier or later? It will turn off earlier. So it look like this. What will happen to M3? Okay. Something like this. Correct? So the switching instant will be modulated by the noise voltage, input referred noise voltage of the transistor. You can think in terms of currents also, right? The current through the transistor is supposed to go to 0, but if it does not due to the noise current, then it will turn off later or earlier. Okay? So this noise is being compared to the, let us say this, let us assume this was a sinusoid. This was the ideal sinusoid. For now we will assume that the LO signal is a sinusoid. And if I have some noise signal Vn of t, what you will have to do is zoom into this region. Okay, and you will have a zero crossing here. You will need to find out how much that zero crossing has moved, right? So this, let us say this was the original sinusoid and the Vn of t was passing here. So the original zero crossing will move to this point. Okay, that is how much the Vn of t has changed the time. And let us say this was some delta t. Okay, how do you find out delta t? Since it's a very, very small portion, we can apply a linear approximation at the zero crossing instant and figure out what delta t is in terms of the voltage waveform. So, yes. Sorry? Yeah, I know. This is just a representation. That is all. Okay, don't worry about this. Don't worry about what I said earlier. This is just some Vn of t. Okay, delta t could be positive or negative. So delta t, I can write it as Vn of t over the slope of the curve at the zero crossing. How do I find out the slope of the curve at zero crossing? That will depend on the kind of waveform you are using. Okay, if you assume it's a voltage is a sinusoid, it is very easy to calculate that slope. This is the slope at the switching instant. Okay, how does this get translated into the output current? So what we will do is, we will assume that the devices switch instantaneously anyways. It is just that at the zero crossing point, the zero crossing point changes due to the noise, but the devices themselves switch instantaneously. So the output current waveform looks more or less like a square wave, except it will now no longer be a symmetric square wave, right? It's the zero crossing points of the square wave get affected by this Vn of t. So the instant at which the current waveform switches will get modulated. The way we analyzed it is we actually looked at the current as, let us say the tail current was IT. It was IT multiplied by a signum function S of t, right? And an ideal symmetric square wave. So let us say this was S of t. However, what I know is that I have these regions over which it could switch depending on the actual value of Vn of t at the switching instant. So this is delta ti plus 1, and so on. Right? At each switching instant there will be a different delta t. So let me call this SR of t because it is not the original signum function, and I can decompose this, okay, into an ideal signum function. So this was plus 1 and minus 1. And what else? What will be the other extra component which I am adding? It will be a series of pulses, right? What will be the amplitude of these pulses? What is the amplitude of the square wave? Will it just be the amplitude of the square wave? Here the square wave is plus or minus 1. What will be the height of these pulses? So remember that the pulses, because the pulses are changing from minus 1 to plus 1 and plus 1 to minus 1. So the overall change affected by these pulses is going to be plus or minus 2, right? So I am not showing the sign here, but you could have I don't have space to show the sign here, but you could have a negative pulse also. I'll call this some pulse train P of t. This is your S of t. So what I said is SR of t. This is your non-ideal pulse square wave is S of t plus P of t, which is the pulse train. What is the height of the pulse train in the current domain? If you look at the differential output current, what is the height of the pulse train? I call that Pi of t is the output current pulse train. What is the height of this? It will be 2it. Okay. What is the basic fundamental rate of this pulse? It's going to be 2, right? 2 FLO, because it is happening at every zero crossing. At a rate 2 FLO. What is the width of this pulse? It changes from time to time, and we know the width is nothing but Vn of t by S, right? Vn of t by S. So this width delta t. So these are the characteristics of this extra pulse train. So if you want to find out more about this, now we have a good idea of what we need to do. Right? We know what happens with an ideal S of t. Now we need to find out what happens with this. So before that we need to find out some things about, for example, we have not found out S yet. So let us do that first. We'll first figure out, if you have a sinusoid at the input, what the value of S is. So let us say VLO of t was capital VLO. Sin omega LOT. In fact, let us say it was plus or minus. So on one side you are giving VLO sin omega LOT, on the other side you are giving minus VLO sin omega LOT. Which means the slope. So of course, first of all, we are primarily interested in the differential signal. VLOD is sin omega LOT. The slope is d by dt of VLOD. cos omega L of t. So S is the slope at the zero crossing point, which is 2 VLO omega LO. Okay? Okay, so this is the value of the slope for a sinusoidal signal. Obviously, if you have a square wave signal, this slope will change. You will have to figure out what the slope is. So now what we are going to do is find out the average value of this current over one period. Why do we want to do that? That will give us an idea of the low frequency noise, low frequency content. Of the output current. So I'll call that ION. What is that? That's 2 by T integral 0 to T of I out N, right? What we have figured out. What is that? It's 2 by T times. What is the pulse height? 2IT times delta T. Correct? What is this? 4IT times. What is delta T? So Vn. So at that instant, I'll call it Vn at low frequencies by S times T. So it's, what is S times T? What is S? 2 VLO omega LO times this T is TLO. So what is that? 4 pi VLO. Okay, so this is your low frequency content, right? If Vn has a certain behavior, your IO has this similar behavior. Actually, it's as it turns out, IT, VLO, pi are all independent quantities. So ION of T will be this quantity times Vn of T. ION of F will be this quantity times Vn of F. It doesn't matter whether you look at it in the time domain or the frequency domain. So let us say in the frequency domain, ION of F is times T1 of F, but the only difference is you will have sampled images because this pulse rate is happening at twice the LO frequency, right? We can't just straight away write this. This is valid only for low frequencies. In reality, if you want the totality of the output noise, so I'll just say except sampled images at 2 FLO or 2 omega LO if you are plotting it with respect to the angular frequency. Because the basic idea is you can look at this pulse train because these delta T's are very small compared to your TLO, your LO period. You can say that this is practically an impulse train. That is why you are able to convert this to a impulse train in the frequency domain also, and you look at sampled values at 2 FLO. So for example, if you are interested in flicker noise, let's say this was F, ION of F, you will get some noise here, and let us say omega LO. Because we have considered a single balance mixer, you will get this LO component also, and 2 omega LO, you will get something like this. And so on, right? You will get these sampled images at every 2 omega LO. So what is this? This was the quantity we just derived, which was IT by pi Vn of f, okay, which is the value we derived for flicker noise. You can do the same thing for thermal noise also. It will give you exactly the same thing. There is really no difference. So if you were actually to write it out in terms of the pulse train, In out of t, the total value, k equal to minus infinity to infinity, 2 IT by S Pn of t times delta of, this is the pulse train in the time domain. In the frequency domain, again this will be a pulse train. Okay. K equal to minus infinity to infinity, Vn of f f minus 2k FLO.